Good afternoon. Welcome to Unleashing the Power of Machine Learning with InterSystems. I am Marta Manzin. I'll be presenting today with Woodlock and MacLeod. And today we'll be going through the whole workflow of creating a machine learning solution with InterSystems products, and we'll be looking at a whole variety of different tools and services. But before we start with that, I want to share something exciting. You might know that Gartner named InterSystems a visionary in its Magic Quadrant for database management systems, but specifically, they praised our support for AI and machine learning, and they said that we dramatically enhanced our capabilities for in-database processing. Now, these are very nice words. Today, we're here because we want to show to you what they mean in practice with a series of live demos. So like any good demo, we're going to get started with a use case scenario. This is a hospital census application. It has a series of patients listed with some demographic and clinical data. And the admins of this hospital are concerned about the possibility of patients having a stroke. And they asked us to take all of the data in here and use it to predict a probability of stroke for every one of them and display it in a new column in this user interface. So we're going to need to take a couple of steps to help them. First of all, we'll need to obtain and pre-process some data to connect the patients to obtain some data about the patients and also pre-process it to make it more suitable for a machine learning use case. And then we'll need to train an actual machine learning model to solve this problem. And last but not least, we will enhance this application by changing its IRIS backend to display the predictions we've come up with. So this is a very busy agenda, and as I told you, we'll be using a lot of different InterSystems products. We'll get started on our Cloud SQL portal, where we'll do some feature engineering, and then we'll create a first model using IntegratedML. And then we'll leverage our IRIS data into a Jupyter Notebook, and we'll create a more advanced model in there using Python, which is the state-of-the-art language for this kind of problems. And last, we'll go back to IRIS, and we'll use Embedded Python and IntegratedML to bring in the model that we've created and update the actual application. So without further ado, let's get started with feature engineering. As I mentioned, we'll be using our Cloud SQL server because it allows us to spin up an instance of IRIS very quickly on demand with no installation required on our machines and very little configuration. In the interest of time, I've already created a deployment for us, and I also have loaded some data. So the data I have for you today actually consists of two tables. I'll show you the first row of each of these tables, and I hope you'll help me do some feature engineering on them. The very first one is a table of patient data. Each row is a patient, and we have some information such as their date of birth, height, weight, their zip code, and the most important one at the bottom, the stroke. So whether they have had a stroke or not, that's our Boolean label. The second table we have is very conveniently a list of zip codes with their corresponding location, and each of them is categorized as urban or rural. The very first thing we'll do is we'll join these two tables together because actually machine learning models like to receive all of their data in one individual table. And the second thing is we'll see if we can use the data we have to come up with some more useful features. So for example, I see that this patient here was born on October 16, 2003. Do you have any idea of what other piece of information I could infer from this data that might be more useful to find their chance of stroke? Their age, exactly, thank you. So we'll be calculating the patient's age, for example. We can calculate their BMI using their height and weight, although I see that actually the weight of this patient is 0 pounds. Are they just very skinny? What's going on? Do you have any idea? Well, it turns out that our data is just bad, and that happens all the time in machine learning, and we'll have to deal with it. So our course of action is going to be the following. We are going to compute the age of each patient from their date of birth. We're going to include their residence type, urban or rural, by matching the two tables. And last, we are going to compute their BMI, accounting for the missing data. And all of this is going to happen on our Cloud SQL portal with one single SQL statement. And if this looks intimidating, it does exactly what I just described. It creates a new view for all of our process data with the calculated age, the residence type, and the BMI. So let's go ahead and do that. OK, so this is the deployment I've created for you. And in this very first page, we actually have some information, such as the host name and port of this deployment. We're going to use that later to grab information out of here. But in the meantime, we're going to go to our SQL query tools. And as this loads, you'll see that we already have our two tables loaded up here. And we're actually going to copy and paste the statement we saw in the slides to create our process data view. I'm going to execute that. You can see that our process data is available. And actually, I'll show it to you. So I'm going to select all from stroke data processed. I'm sure I'll make plenty of typos. But this one worked. And you can see that here we have our age, which has been computed for every patient. We have the residence type. And we have the BMI, which is occasionally null when there is not enough data to compute it. Great. So let's see what is next. We're actually going to build a model using IntegratedML. And IntegratedML allows you to build an initial model using just 4 SQL statements, which makes it very convenient and lowers the barrier to entry if you're trying to figure out if machine learning is even a viable solution to your problem. The other thing that's cool about it is we like to say that IntegratedML brings the ML to the data. So you don't actually need to take your data and ship it to a third-party outside provider, which could basically bring additional costs. And it could also bring some issues if there are any regulation limiting the sharing of sensitive data. You can just do everything within your IRIS instance. And on top of that, we're actually going to do all of this in the same cloud portal that we just used. So that's super convenient. As I mentioned, IntegratedML uses 4 new SQL statements which were introduced on purpose, and they correspond to the different steps of implementing and using a machine learning model. So we start with creating a model, defining what the problem we're trying to solve, and then we train it with our training data. Then we do a sanity check to make sure that it's actually any good by validating it. And last, we can actually go and use it in the field by predicting new probabilities. You might notice I'm saying that we'll need to train and validate our model. This means that we'll need to take a little bit of data aside and not use it for the training so that we can then use it to check if the model is actually good. So we'll need to do a split of our database. And I'm actually going to take aside about 20% of our data for validation. So let's go ahead and do that in our cloud portal. You can see that each of these patients actually has an increasing ID. So I'll take all of the IDs that end in 0 or 1, and I'll use them for validation. And all the other ones will go into training. So create a new view. And that's going to be, I'm going to call it stroke eval. I'm going to use a modulo operation. And I'll take all IDs ending in 0 and 1. Great, and we can see that our view stroke eval has been created. And I'll create a second one called stroke train with all of the other IDs. OK, now that they're both in here, we can head over to our IntegratedML Tools tab and create our model. So our model name will be stroke model. And I'll train it on the stroke train table, unsurprisingly. And I'm going to predict our stroke bit, which is a Boolean value of whether the patient has had a stroke. And I create the model. You can see that the UI generated a SQL statement, which is being run. You can see it right here. Now I can go ahead and train this model I've just created. So I select it, and I call it stroke trained. And I'm going to train my model. And you can see here that our training run is starting, and that will take a little bit. But in the meantime, we can actually look at what is going on under the hood. So we have a third-party provider called H2O in this case, which is installed locally, and that is doing the AutoML work for us. So the provider is first doing some feature transformation, dealing with null values, which we saw we have some nulls. And then it's trying out multiple traditional models, such as boosted trees, logistic regression, and it's selecting the best models among these, and it's ensembling them together. This is a specific machine learning term. It's ensembling them together to get a one better, more high-performance model. So if we go over now to our portal, we can see that our run is completed. And now we can check how well we've done. So we go over here to our validation tab, and we can refresh our page and select the model we just trained. And we're going to check it against our stroke eval table. And I'll call this stroke eval. That's our validation run. That should only take a couple of seconds. Great, completed. To see the results of our validation, we head over back to the SQL query tools, and we select a table in the information schema namespace. And it's called ML validation metrics. It's a very sensible name. And if I oh, and of course I need to select from. All right, there we go. So here I'm displaying the metrics for the model we just trained. And there's a few of them, and we can see that the accuracy is 90%. So at this point, I could tell you, look, 90%, this model is great. However, there is one catch. So let's look into it together. The thing is that if you look closely at the data that we used, you'll find that only about 5% of the patients in our data actually had a stroke. So this is a needle in a haystack problem. And we have a model that performed with 90% accuracy. Can any of you suggest how I could build a model that would have 95% accuracy, knowing this about our data? Exactly. So I could just say no one had a stroke, and I would be 95% accurate, but that really wouldn't be very useful. So the takeaway is that accuracy really isn't a good metric for a needle in a haystack problem like this. However, there are better metrics, and we can look into that. What I've plotted here is called the confusion matrix. I have plotted all the patients who actually had a stroke and the ones who did not have a stroke. And then against that horizontally, I have the prediction that our model made, which means that we actually had a pretty good true positive rate, people who are at risk of stroke and were caught. But then we also had quite a few false positives, so people who did not have a stroke but were classified as having one. And really, the performance of a needle in a haystack problem is all about this trade-off. We could use this model to get more true positives, but we would end up having more false positives. So how many false positives do we need to put up with in order to have enough true positives? We can actually plot this trade-off on a chart right here, true positives versus false positives. And our current implementation stands at about that dot, 57% true positive rate against 8% false positive rate. We can use this same model to get more true positives at the expense of more false positives. Now, in a perfect world, our curve would look like this. We would have 100% true positive rate immediately without any false positives whatsoever. This isn't really realistic, but we would like to get as close to this as possible. And so, a good metric for the performance of our curve, which you see again right here, is the area under the curve. I shaded it. You can't really see the shading in here, but the area under the curve is 0.87% at the moment. It could get to up to 1%. 0.87 as a total number, it could get up to 1. By the way, AUC stands for area under the curve, a masterpiece of creative naming. You might be wondering, can we do better than 0.87 area under this curve? Yes, with a better model. And I'm going to hand this over to Don Woodlock right now, who will build that model with you.
Okay, great. Okay, so step one, this is the way we picture customers walking through a machine learning project. So step one is to do that feature engineering work. So what are all the things that would be helpful to predicting stroke, in this case, or whatever we want to predict? And we showed you that in SQL. Step two, which is an easy step, is at least use our integrated ML to get kind of a baseline model. So we did that, it only took a couple minutes, and now we have a model that has an AUC of 87. So then the third step will probably be that your data scientists, or all of you in your copious free time, will get into Python, into a Jupyter Notebook, and build your own model and see how accurate you can make it. And then we'll use the model in an application. So I'm on step 3. I'm going to build a custom model in Python. Okay, first of all, if you haven't seen this concept of a Jupyter Notebook, this is the coding environment that data scientists use. And it's somewhere between a mix of an IDE kind of text editor, but also a command line. So it takes a few lines of code in each cell, and it runs those lines of code and shows you the output. And so that's a very nice environment for you to develop machine learning models and explore your data. So I'm going to go through about 10 cells here to build this model. This first cell is this is all Python code, and it's importing libraries that we will use later. And you can see it's running, actually it's hard to see, there's a little number there. We ran the first cell. Okay. Now what we're going to do is pull connect to IRIS. So Marta just created this view that is the source of our model. And so this particular cell will connect to IRIS. So Marta showed you those parameters, the host and port and password and things like that. Probably should change the password after this. Here's our password for our data if you'd like it. So go ahead and connect to that afterward. Okay, so we establish a connection here. And then once you do that, you can just run a SQL statement. There's a library here called pandas. That's what PD stands for. There's a method read SQL query. It takes that connection and a SQL statement, and it runs it. And then it pulls all that data into a local variable called stroke_df. And this variable is it's a data structure called a data frame, which is kind of like a table. So a rectangular structure. You can see the same information that Marta showed. 1 row per patient, all the columns, including our new columns, residence type, BMI, what else did we add? Age somewhere. Yeah, age right there. Okay, so this was Marta's view. The next thing we do is we select some of the columns as the features, which we put into the variable x, and then the label you're trying to predict, it's commonly put in the variable y. So that's what this cell is doing. And that is from algebra, essentially. Y is a dependent variable, and x is all the inputs into that. Now what we're going to do is similar to Marta, but we'll use a library to do this, is we're going to split the data between trained data and testing data. Otherwise, you'll never know how good your model is, because you can't measure it against the same data that you train on. It's a little bit like teaching somebody how to take a test and then you give them the actual test, and they've just memorized the answer. So you kind of have to teach them in one way and then have a different way of testing it. So you can see in the ID column, for instance, it's not 1, 2, 3, 4, 5. It has selected a random assortment of rows for the testing data. Okay, we're going to use one of the many Python, or one of the many libraries in Python to do machine learning. For tabular type projects, the best, in most people's experience, is gradient boosted trees. And XGBoost is one of those libraries. And I'd be happy to explain what that is afterward, because I'm sure we'll run out of time. So that is what this library needs, though. It needs to know what categorical features you have. And a categorical feature is like a text feature or a number that's not really a number. Like zip code's a good example of a number where, I don't know, 2,000 is not twice as much as 1,000, as an example. Or a string like gender or things like that. So the way you tell XGBoost about it is the data type of the column. So this is reassigning the data type to be called category. This is instantiating the model down here. You can see the model is an XGBoost classifier. And all these parameters, this would be an advanced class we could do next year, on hyperparameter optimization. But these are all the parameters that I ran this model for about 5 hours to find the best parameters, but that's kind of the machine learning process. And this next cell actually trains the model. Okay? So that is running through and training the model. These are the AUC numbers on the training data, which will be higher than the AUC numbers on the validation data. But we got to 89% versus 87% in integrated ML. So we can take a look at the predictions. Let's get out of this. OK. So you can see now we have a probabilities column. And so this model predicts the probability that this patient will get a stroke from 0 to 1. Basically, I've sorted it from top to bottom. And you can kind of see by sight whether the model's any good. 5% of our patients have strokes. So if this was randomly laid out, it'd be 1 out of every 20 patients would have a stroke. But you can see it's more frequent on the top of the list if you sort it by probability. So that's what you want to see. It's not a perfect model, you can see, but you see more frequent ones than every 20 rows. This gives you your official AUC score of 89, which is, as I've indicated, pretty good with an exclamation point. And then lastly, what's nice about these models is they can tell you which features are most important in constructing the tree. So you can see the #1 feature is age, which I think is understandable. I don't know why it keeps doing that. #2 is, let's see, whether this patient has heart disease. And funnily enough, the #3 is whether the patient's ever been married. Okay? So I don't know if that helps or hurts, I forget. But what do you guys think? If it helps or hurts. Why would that be? Does anybody have a guess? Survival insurance. Could be, could be. I was thinking it might be a proxy for age, right? Because kids don't get married. You know, your chance of ever being married, it doesn't have divorced in here. That could skew it a little bit. But if you've ever been married, you know, the older you are, the better chance that has occurred. So it could be related to age, probably. The thing about machine learning is it's generally not cause and effect. It's generally correlation. So you get a lot of these like related things, but it still helps you build a model. My last step is that we built a custom model. It's a little bit better than integrated ML, and we're saving it. And then Alex is going to use it in an application, and she'll show you how that looks. Okay.
All right. Thank you, Don. Let's see. Let's go back here. I have a couple of slides, and then we'll go to town on ObjectScript. So Marta showed you the screenshot of the application we have, that hospital census, right? That has kind of the demographics, and then it had a column that wasn't filled in yet for the probability. Now these guys have created 2 different models, so we'll take 2 approaches of predicting whether a patient's going to have a stroke or not. The code that's there is basically the UI is written in Angular, and it uses REST to call back to the IRIS backend, right? So what we'll do is, in the first step, we'll look at just changing, so it's basically just a SQL statement that populates the table on the front end, right? So we'll change the SQL statement to include the probability call to get that column populated. So that's simple. That's using the integrated ML model that Marta created, which is a little less good than Don's model, right? So then in the second step, what we'll do is we'll flip it, and we'll use embedded Python, load in the model that Don just saved, and run that, to populate that same column. So that way you get the 2 different approaches, right? So this is approach 1. I'll show you in the code in a second. But approach 1, basically you don't really need to know anything about machine learning, right? So Marta used the UI and the cloud to generate the model. And then all I have to do is, if I know SQL, I can just add another, basically, column here that uses this probability statement and tells it which model to use and what column to predict, right, and what to call it. And that's it. I don't have to do anything else. It'll send it back through the REST service to the front end, and it'll populate that column. Approach 2 is a little bit more complicated, but it's kind of cool, because now you're in an ObjectScript backend in IRIS, right, and you want to do Python things. So there's a way to communicate between the ObjectScript portion of the code and the embedded Python piece running in the IRIS kernel, where you don't have to call out, but you hand off between what looks like native Python code in the same Visual Studio environment. And we make it a little bit easier for you to pass things back and forth between the 2. Right? So in ObjectScript, there's this syspython class that provides you built-in constructs. So you can, for example, build a Python list of all your patients, give that to the Python method, right? It sticks it into a data frame, loads up the model, does the probability predictions, and then sends it back to the ObjectScript portion, which returns to the front end. So it's kind of neat. It takes a little bit to get your head around it, and I am not a Python or machine learning person. I'm an ObjectScript girl through and through, but then I just steal code from Don, copy and paste over, and it just works. So we'll take a look at this, and I'll show you how it works. So right now, let's see if I can make this a little bit bigger. A little bit. All right, so this is the census application, right? So you see your demographics here, and we have this probability stroke column that doesn't have anything in it right now. Now, if I go to my visual code, I'm just showing you, I'm not going to teach you Angular in this class. And I've prepared the code so that you don't have to see me type, because I'm not that fast and I get nervous and I make typos, but we're happy to share any of this with you afterwards. But basically, right now a call comes in through REST, and it routes it to this integrated ML method. And the method, you don't need to look at any of the error trapping or something. It basically just runs a select statement, right, on the columns that are already there. So now if I comment out this line that says add this probability statement that you saw in the slide, right, then it should use that to populate the probability stroke column. So let me compile that and refresh the front end. And now I get the probabilities here. We kind of cut it down to just 5 digits. And I could now sort to see where do I want to focus my efforts, who do I want to intervene on, where do I want to send my resources. Right? Now, alternatively, let's say, all right, Marta, this is nice, but I want to use the better model that Don built, because he actually spent all the time, so we don't want that to go to waste. I report him, so I have to say that. Right? So now let's switch the REST call first. We'll basically tell it to go to the embedded Python method instead of the integrated ML one. I told you I'm an awful typer, especially with an audience. Right, so now it calls the embedded Python method. So we'll scroll down past all of this. So here's embedded Python. It basically does something very similar, but it pre-built a couple lists of patients so that I can pass it to the Python code, right? So it runs the same query without the probability statement. Then it uses the syspython built-in functionality that I mentioned on the slide to build a list of patients that sticks these in. And then it basically passes them off to a Python method that's tagged here. Like you see, the language is Python, right? And now we're in Python land. So now you see a similar import statements that Don had to get all the libraries in. I'm creating a data frame first from the list that I got from ObjectScript, right? And I have to kind of tell it what the columns are and how they're categorized. Then I import or load this XGBoost model that Don created. Now, if this part of the demo fails, it's his fault, right? Because he created this model, so we'll see what happens. So I'll import that model and then run the predictions based on that model. And then I pass it back as a list to ObjectScript, and ObjectScript takes it to the front end, and we're done. So now let's compile this again. And the ta-da effect on refreshing. The ta-da effect on refreshing the browser is not so great. Look at this. I put a hang in just so you get nervous. But you know, now the probabilities look a little bit different if I sort, just because it's using the other model, right? So it's not exactly the same anymore. But it's pretty neat what you can do with honestly not knowing that much about machine learning. Someone has to know, but not me. So let's just recap how we did this, right? So you have two options, right? And it depends a little bit on your use case. Maybe, you know, 87 AUC is good enough, right? If you just want to sort things, you're not making any clinical decisions, you're kind of looking at resourcing or overbooking or any use cases like that, maybe that accuracy is fine enough. You're good with integrated ML, and you just use that, and all your people need to know that are building applications is SQL, right? And you don't really need anything beyond that. Or you want to use Python and have a better model, you need better accuracy or AUC, right? And then you have the other option. Now, in both cases, though, you don't have to export things, you don't have to create these huge CSV files, give it to a data scientist team, wait 3 months, get it back, and then embed it in the application, right? Everything runs directly in IRIS, other than the little bit of work Don had to do. But the runtime is all within IRIS. You're also not calling out through any gateways to an external coding environment or anything. It happens right there. So we're bringing ML to the data, whichever way you do it. So you saw actually a lot in this 40 minutes, 35 minutes, right? Because we showcased a bunch of the cloud services that we have that make it easier, right? Let's say you're not using the cloud service, but you have IRIS on-prem. You can still do everything we did, but integrated ML is basically the bunch of SQL statements that Marta showed you get created from the cloud UI, right? So you have to just run those and kind of familiarize yourself with the 4 statements to create the model, train, validate, and then predict. In the cloud, it's a little nicer because you get the UI with all the drop-downs and such. So we have that. We have, you know, embedded Python makes a huge difference, I think, not just for usability and where you can run the code, but also, frankly, for skill sets, right, of who you can hire to write these applications for you. I think everyone who is anyone except for me can write Python these days. And with that, we'll open it up to questions.
Questions?
Yes.
Yep.
Yes.
It's more a question on the input data. Why have you excluded the history of stroke before? And if the patient, for example, if they have one of their family members having a stroke before, and if they already had a stroke, maybe this is their second time.
So the question, just to repeat the question, is on the data input, why do we exclude data whether the patient had a stroke before or any family members have a history of stroke?
Yes, so actually we're not excluding the stroke data. What we're using is we are using already known data of patients who have or had not had a stroke, and we're looking at their other clinical and demographic information and think, could we have predicted that stroke knowing all their demographic and clinical information? So the stroke in this case is what we call a label, and it is what we are trying to predict, knowing everything else.
But in terms of like prior strokes or things like that this wasn't really a class on predicting stroke. It was a class on kind of what the process was. So we just grabbed some data set from Kaggle, actually, and used that. I think that, part of the process is feature engineering. What are the, and that's where subject matter expertise matters. What are the key predictors of stroke? What are the risk factors? And trying to get that all into your model will only make the accuracy better. Okay, yeah.
Yes.
Oh, we have a microphone.
Oh.
Are the trained models exportable for source control and deployment and so on, or do you have to train on the actual
Can you hold it
production?
a little closer? Sorry.
Are you able to export the trained model into source control for automatic deployment and stuff like that, or do you have to train them on the actual production instance?
You're talking about the integrated ML piece?
Well, the result of the training, the actual trained model, I suppose you could export it to a file.
Yes. Sorry.
You can go.
Well, there were two trained models. So the Python one, the one I did, it just saves it as a JSON file. So you train it on your production data or whatever your good data is, and then you save it as a JSON file, and then you can incorporate it into something else. So you could train it on a copy of your data, that sort of thing, get a good model, and then move that model into production for the production use.
So you're able to export it.
Yeah.
I have two short questions. The first one is about data cleaning. I assume from what we're seeing that this is going to help people who don't have access to data scientists so often, so we can do things faster and get results faster. But data scientists in general are very protective about their models, etc. So linking to your question, if somebody has a bit more experience in data science as a data scientist, can they import, export? Can they compare to challenger models? Can they decide effectively what model they're going to apply to this? Is that possible?
I don't know why it's bad.
It's really bad up here in terms of hearing.
But I think the question is, can your data scientists query for the model, export it, work on the model that you created?
The ones from the integrated ML.
We do have some PMML support, if that is what you're asking for.
So,
I'm asking, can somebody choose effectively what model they're going to use after maybe comparing it to other challenger models?
So, a couple things. One is we never really position this as you don't need data scientists. Mm-hmm. I think that's going too far to say something like this. We position it kind of like we did today. You just get started. It's pretty easy. Get a baseline, and then no doubt your data scientists will want to take it further. At the moment, if you press the log button when you're training, you get a feel for what models were selected by the AutoML provider. Okay. In this case, H2O. So that could be helpful in terms of a starting point for your data science work. The other thing you can do actually is H2O is also a library that you can use and have it use AutoML in that way to get you started.
Okay, you've already answered the second question, so thanks.
Neil, yeah.
Yeah, so...
actually, don't use the mic,
I
Neil.
won't use the mic.
Because you're loud.
Yeah. Thank you. This is really great. The question I have is that in my team, only about a quarter of them actually apply. The rest are Julia or R.
Okay.
So are there thoughts for including additional languages that data scientists may be using, particularly Julia, but also R?
So for R, we already have a gateway. So you could call out to R, have your libraries live there and call out. Julia, I don't know of any plans.
So, yeah, in terms of embedded languages, I don't necessarily know that we have plans for those, like Alex's part. But my part, they can build models in R, save them as JSON files, and then she can pick it up in a very similar way. Yeah. Yeah, as using the R gateway or
Not
something
me
like that.
personally, but
Yeah.
your people.
But that concept. I mean, I never like picking favorites when there's language things, but Python's kind of on a tear, so you'll find people eventually. Yeah.
There was a question over here.
Yep.
Is the code also available online?
Code available online.
So right now it's in an internal Git, but we can make it available. There's no secrets here.
Yeah.
The other thing I wanted to point out is that we did IntegratedML through the portal, but actually you saw how those SQL statements were being generated in our UI. You could handwrite those and run them in your IRIS instance if you have a version of IRIS that supports IntegratedML. So you don't need to have the cloud and the cloud interface to do that. There are many versions of IRIS that already support IntegratedML in the SQL editor.
Including the community version, so you can actually get access to IRIS community with IntegratedML enabled. So if it's a good lab to run this exactly example.
Any other questions?
Last question,
Yep.
but it's not a development question. I just want to know how easy it's going to be to have this data embedded into TrackCare or brought up to TrackCare as results to the doctors, for example, as an algorithm to say that this patient is having a high probability of getting a stroke in the upcoming, let's say, 6 months, 1 year, 3 years.
So the question is, how easy is it to get this technology embedded into TrackCare for actual clinical use? I believe that right now IntegratedML is offered in IRIS and IRIS for Health, and not yet in HealthShare and TrackCare.
Yeah, but
Sorry.
Okay.
Yeah.
So I don't know if you know something. Most of the workflow that we've discussed relative to TrackCare is migrating the probabilities, let's say. So anybody above X probability, migrating that into TrackCare as an alert. Yep. And then once it's an alert, there's a variety of things in TrackCare, as you know, that you can do with it. Show it on the patient banner, and work lists, reports, things like that. So that's been the main workflow integration we've thought about. Okay. Great. Thank you very much. Appreciate your time.
Thank you.